I'd like to repeat the derivation that we just did, but I want to do it using more the logic of the second proof that we gave of Newton's theorem. So for that second proof, what did we do? Well, we started off and we said, let's perform the symmetry transformation, but we'll do it with a parameter that depends on the coordinates. So in this situation, we would shift t into t plus epsilon of t. If we do that, what happens to x of t? Well, x of t goes into x primed of t, which is equal to x of t plus epsilon x dot. So far, this looks exactly like what we had before. The difference comes when we start to differentiate. So x primed dot will be equal to x dot. And now when I differentiate the second term, I'll get epsilon x dot dot. That's what would have had before. But I'll also have an epsilon dot x dot term. This is new, and it appears precisely because the parameter of my symmetry transformation is now being allowed to depend on time. So let's work out what the action looks like. So the change in the action will be an integral dt times by the change in the Lagrangian. And we know that the Lagrangian is a function of x and x dot. So this will be dl dx times by delta x plus dl dx dot times by delta x dot. Okay, let me just remind you, I think that you know this, but the Lagrangian that we're studying is for a particle moving in a potential, and that's the form of the Lagrangian sitting over there. Good. So this will be an integral dt. Now dl dx, this is just going to be minus dv dx. Then times by delta x, this is epsilon x dot. And then plus we've got the dl dx dot. Well, the dl dx dot is going to be nothing but mx dot. And then delta x dot. And delta x dot, well, let's just be completely clear on this. So delta x dot, that's the change in x dot. We can just read it off from there, okay? So this will be nothing but epsilon x dot dot plus epsilon dot x dot. So just grouping the terms, what do we have? Well, we have an integral dt. Then we've got epsilon. And what does the epsilon multiply? Well, it multiplies mx dot x dot dot minus dv dx times by x dot. So those are the terms that multiply the epsilon. And then we've got a term that multiplies epsilon dot, and that term is just mx dot squared. Now remember what we're shooting for. This should be an integral dt times by the conserved charge times epsilon dot. This is how the change of the action was in our second proof of Newton's theorem. And, well, it's looking promising because this term has got an epsilon dot, so that looks good. But this term does not have an epsilon dot. So that term we'd like to rewrite somehow. And to rewrite that, note the following, okay? And let's maybe do it a little bit down below. So that term, we've got m x dot dot minus dv dx times by x dot. It's not very hard to see that this is nothing but d by dt of m over 2 x dot squared minus v. Okay, so if I take the d by dt on the first term, because of the squared, I'll get a 2 coming down, and when I differentiate the x dot, I get x dot dot. So indeed, I'll get mx dot x dot dot. And then minus, the potential only depends on time. There is dependence on x, so it'll be dv dx times by x dot. Good. Okay, so I want to use that now. And I'm going to use that in here. So I've got an integral dt. Let's write this as epsilon d by dt of m over 2 x dot squared minus v. And then I've got plus the epsilon dot term mx dot squared. And in fact, the natural thing to do now is to integrate by parts, okay? So that's what I'm going to do. I'm going to write it in a very pedestrian way, but that's okay. I'm just integrating by parts, okay? So what is this equal to? This is equal to an integral dt of, we can write this as d by dt of epsilon m over 2 minus v. And now let's see what we get. When this d by dt, oh, sorry, I dropped a few terms there. Let me put them in. So this should be an x dot squared minus v. Okay. When I differentiate this product here, when the d by dt acts on the second bracket, I get the term above, but I don't have the term with the d by dt acting on the epsilon. So I'll just subtract off epsilon dot m over 2 x dot squared minus v. Okay, so when I take the time derivative of this first term, I've got epsilon times something. So there's a term which is the epsilon dot times the second thing. That will cancel against the minus term here. And then there's a term which is epsilon times d by dt of the thing that sits there, and that's the line above. So that this quantity over here is exactly the same as that quantity over there. And then let me not forget the second term. This is plus epsilon dot mx dot squared. Good. Now, this term over here, I drop. Why do I drop it? Well, it's the usual thing. It's a total derivative. So it depends only on the endpoints. Okay? Only on the initial and final time. So I don't have to bother about that. And if I keep the terms that are left, what do I have? I've got an integral dt. I've got epsilon dot, and then what multiplies it? I've got minus m over 2 x dot squared plus v, so that's from that bracket. And then I've got plus mx dot squared. And now I just want to add the first and third terms in this expression. Mx dot squared minus a half mx dot squared is a half mx dot squared. And then I have plus v. And indeed, we see we have exactly reproduced the conserved charge, the Hamiltonian, as the coefficient of epsilon dot. And this is exactly what we should have done. Okay, so that was just repeating the example that we did, but using more the logic of the second proof of Newton's theorem that we gave. I hope that now you've got some idea of what Newton's theorem says. It relates symmetries to conservation laws. I hope that both in mechanics and field theory, you can derive the conservation law associated to the symmetry. And in fact, this is a very general argument, well worth mastering. Any conservation law that you will meet can be explained in this way. Some of you may have met some topological conservation laws, which looks like you can't derive them by a Newton argument. That's not true. In fact, there's also a Newton argument for those conservation laws. It turns out all conservation laws that you want to understand can be understood in this way. And that completes our discussion of Newton's theorem.